inverting op-amp circuitry, basic inverting op-amp circuitry, and in particular the op-amp circuitry with the reference voltage. We could draw a simple op-amp circuitry. Okay, we have R2, R1, V out, V in, and here is non-inverting input. Remember, every time you draw this circuitry, you infer there's a ground level somewhere. Okay, every voltage output or input or any values it refers to the ground potential. We assume it's ground potential. Here is 0 volts, and this is in at ground potential. And what the transfer function looks like for this, that's pretty straightforward because we know here and here same potentials, here's 0 volts, and we follow the current flow from this way to that way because the current cannot flow inside the op-amp. So we just follow the current. We have V in minus 0 volts, minus here, divided by R1 equals 0 volts minus V out divided by R2. Okay, and rearrange this one where we can V in divided by R1 equals minus V out divided by R2. And we can move the V out to this side and rearrange this. We have V out equals to minus R2 R1 V in. Okay, so this is the basic equation we all know. It's very straightforward. So the signal will be either amplified or attenuated based on the R1 R2 ratio, and the phase will be 180 degrees between the V in and V out. Okay, let's think about a special case. If this node is not 0 volts, not 0, like the ground here, it's a VR, a reference voltage, what that looks like. Okay, as straightforward too, we have VR here, this node and this node are same potential, so this is VR now. So we follow the same equation. We have V in minus VR divided by R1 equals to VR minus V out divided by R2. Same idea, we can rearrange these equations. Let's move the V out to the other side. V out minus VR divided by R2 equals minus V in minus VR divided by R1. So V out minus VR equals minus R2 divided by R1 minus times V in minus VR. Okay. Now you can compare these two formulas here. This one and this one. Okay. Here it looks pretty similar. Okay. The only difference is basically the same equation. Only difference is everything output and input in standard reference to 0 volts minus 0 here or minus 0 here. It refers to VR, so the VR is a reference voltage, or we call that virtual ground. It depends on what you want to count. Okay, so this equation is very same. So all that we are doing is add a virtual ground, then everything, both input and output, is reference instead reference to 0 voltage and reference to VR voltage. And the equation is exactly the same. Okay. This turned out to be very useful in modern electronics, in particular when you have a single power supply. I will talk some examples later. And another way to look at this is you can rearrange this to a different ways. And we just we can move the VR to that side. We got one R1, R2, R1, V in minus VR, so plus VR. Okay. And V out equal to, put this inside the bracket, V R2 R1 V in plus R2, R1, VR plus VR. Okay, so V out equals to minus R2, R1, V in plus 1 plus R2, R1, VR. Okay, now look this transfer function. Okay, it looks very familiar too. This basic linear equation, right? F1 equal to ax plus b. Okay, so a is a slope, is here, minus r2 r1, and b is offset, 1 plus r2 r1 times vr. Okay, if you understand this based on your circuit design, the requirements of your circuit, then you can design a linear transfer function circuitry. Either want to do an offset or you want to do an amplification or attenuations. Basically, you just place a R1 to value and VR values. You can realize a lot of special requirements. Okay.